water is the ability to dissolve a wide range of organic and inorganic molecules. And because of the ability of your water to form hydrogen bonds. Okay. So normal pH of the blood, 7.35. That actually is, this is already acidosis. And pH is 7.45, that's already alkalosis. Because your blood pH is 7.4. So anything below 7.4 is acidosis, and anything above 7.4 is alkalosis. Okay. So you have here your water molecule. On the side of the hydrogens, you have a partial positivity. And on the side of your oxygen, you have a partial negativity. Now in this case, your water is a dipole. Positive, negative. It's a dipole. So there you are. It's a dipole. Because of its strong dipole characteristic, it has a high dielectric constant. Okay. Oh, there you are. Ability of your water to form hydrogen bonds. That's very, very important. Because it influences the water to have a relatively high viscosity and a high surface tension and a high boiling point. High viscosity, high surface tension, high boiling point, just because of this hydrogen bond. Because water hydrogen bonded with another water molecule. So there you are. You have two water molecules here. This is one, this is another one, and you have your hydrogen bond. Partial positivity, partial negativity. And there you are, you have several hydrogen bonds created, 4 of them. You have 4 molecules of water around this molecule of water. And it also bonds with other compounds. Like this ethyl alcohol here, bonded with water. And then this can also bonds with other compounds. The hydrogen bond. Interaction with water influences structure of molecules, covalent and non-covalent bonds. Your hydrogen bond is non-covalent, together with ionic or salt bonds, and then hydrophobic bonds. These are non-covalent. The covalent bonds But you will see more often as the peptide bonds created by your amino acids and your disulfide bonds also created by your amino acids. Now these are bond energies. As you will notice, the bond energy between two oxygen atoms is equivalent only to 34 kilocalories per mole. Now, as you go down and up to here, the bond energy increases. So you have here carbon to oxygen double bonded. Now, single bond carbon to oxygen is only 84, but carbon and oxygen double bonded, you have 164. So what does this mean? This means that this one, in order to break this, you need more than 164 kilocalories of energy compared to like carbon to nitrogen, which only requires 70 kilocalories per mole. Okay. Biomolecules fold to position polar and charged groups on the surfaces. Now, since the body is mostly water, chemical reactions are done in aqueous solution most of the time. But there are those that have also reactions occurring in fatty, oily, greasy environment. And the fatty, oily, greasy environment is your on your cellular membrane, which is a lipid bilayer. It's a lipid bilayer. Huh? Okay. So when we say amphipathic means that it has a polar group or a non-polar group. So you have a hydrophilic group or area and a hydrophobic area of the same molecule. Okay? So it says here, most biomolecules are amphipathic. So which means some areas on that molecule has a positive, a soluble area in water, hydrophilic, and a non-soluble area or hydrophilic. So proteins tend to fold in a manner that the hydrophilic groups are all on the surface and the non-soluble in water, the hydrophobic area, are inside the molecule or in the interior. So amino acids with charge group are polar. And surface that does not have any charges is non-polar. Okay? So, we have here hydrophobic interactions. Meaning to say, that the hydrophobic area, in order that they will not be exposed to the water or the water surroundings, the hydrophobic area tends to attract to each other. No? So the group or they hug each other so much so that no water molecules can come in between them. Now that's your hydrophobic interactions. Okay? Water is a nucleophile. And the opposite of the nucleophile is an electrophile. Nucleophiles are molecules which are electron rich. The opposite is electron poor, and that is the electrophile. Now, it should be also remembered that nucleophiles and electrophiles does not necessarily have a formal negative or positive charge. No? You might think that there's so much of electrons, then you need to it's negatively charged. No, it's not. Does not necessarily possess a formal negative or positive charge. It says here that water whose two lone pairs of electrons has a partial negative charge. Partial negative charge. It is an excellent nucleophile. Okay? It is not a formal negative charge. It's a partial. That's why I mentioned earlier about water that the hydrogen is partially positive and the oxygen is partially negative in the water molecule. Okay. Other nucleophiles include oxygen atoms of phosphates, alcohols, and carboxylic acids, the sulfur thiols, your SH group, and the nitrogen atom of amines, of imidazole, and of or the imidazole ring of your histidine. Okay. Common electrophiles include carbonyl carbons in amides, esters, aldehydes, ketones, and phosphorus atoms of phosphoesters. Water molecules exhibit a slight but important tendency to dissociate. Now, dissociation, we have observed in our previous chemistries that strong acids dissociate completely. Weak acids, it dissociates but not complete. Okay? Now, water dissociates, but its dissociation is very, very slight. No? Dissociation is very, very slight. And the constant of dissociation, as you can see it here, would be the product of the concentration of your hydrogen ions times your hydroxyl ions all over your water. That's your dissociation constant for water dissociation. pH is the negative logarithm of the hydrogen ion concentration. So this was introduced by Sorensen. pH equals the negative log of the hydrogen ion concentration. Negative log of hydrogen ion concentration. Okay. Now, for this particular exam, I will not ask you to compute for pH of given solutions. So you can do away with that. But you must remember that this is the definition of your pH. Negative log, logarithm here is base 10. Negative log of the hydrogen ion concentration. Now let's go back to our what we have learned about acids and bases. So acids are proton donors and bases are proton acceptors. Strong acids, as we have seen here, there are hydrochloric acid and you have sulfuric acid as example. But do not use as an example. Now when we ask for bases, because the strict definition of bases, proton acceptors. Proton acceptors. So that is why when we say strong bases, they usually give sodium hydroxide, potassium hydroxide, strong bases. But per se, they are not bases. They are not bases. We call them alkalis. Now, they have basic property. You get that? Because of the OH. And OH are proton acceptors to become water. Diba? You add hydrogen to OH, you form water. Can you get it? So these are alkalis. They have basic property, courtesy of the OH. But to call them as strict proton acceptors, it's not. It is the OH that is the proton acceptors. Like for example, hydrochloric acid. You know, proton donors, the hydrogen is here. It's removed and donated. What about the chloride? What do you call the chloride? The chloride is your base. Because the chloride accepts a proton, hydrogen, to form hydrochloric acid. Do you get it? Sulfate is the base of the acid sulfuric acid. Because that sulfate can accept the two protons to form sulfuric acid. That's the strict definition of proton donors. Acids are proton donors. They donate hydrogen. So what is this? This is the pair, basic pair. Conjugate base, we call this. You know what is the meaning of conjugal, di ba? Conjugate pair. Sulfate is the conjugate pair of sulfuric acid. Chloride is the conjugate base of hydrochloric acid. Do you get that? So just like this, that OH there is the base. It is not this one. It is not potassium. This is not a proton. No, these are alkalis. So the whole thing, no, They are alkalis. Okay? All right. Um, okay, this is an example. Well, anyway, I'm not going to ask you this for computation of the pH, but you know how to do this. You just have to convert this 3.2 times 10 to the minus 4, no, to the power of 10. Okay, that's converted. That's 3.2 to log minus log 10 minus 4. And what is the log of 10 minus 4? It is the exponent itself, 4. Log of 3.2 is 0.5. So negative 0.5 plus, why does it become positive now when that is negative? Because once you remove this, it's a negative 4, and you change the sign of this and becomes positive 4. So positive 4 minus negative 5 is 3.5, right? So there you are. There's how you should do it. No? Now the pOH is very easy. All you have to do is, you know that dissociation of water is hydrogen ions times hydroxyl ions equals 10 to minus 4, 14. The exponent minus 14. Or you can say pH plus pOH equals 14. So if you're able to get this pH, then you just subtract it from 14, you'll get your pOH. Correct? Because this was asked, the pOH is being asked. And what is pOH? It's the negative logarithm of OH. Similarly, when you say, what is pH? It's the negative logarithm of H. Okay? Now, Henderson-Hasselbalch's equation, this is when you are talking about weak acids and buffers. So as I've said, I'll not ask you for any computation at this time, no? So weak acids and buffers. How do you define buffers? Weak acids and its salt. Diba? It is a combination of weak acid and its salt. So weak acid, what can you give me a weak acid? Remember that when it says strong acid, they are going to dissociate completely. Weak acids, they do not dissociate completely. So what?
Carbonic acid.
Oh, carbonic acid, yes. What about amino acid? Yes, it is weak acid. That's why it is being used, protein is being used as a buffer, just like your hemoglobin. Your globin is your globin is a protein. is acting as a buffer, no, in the blood plasma. Huh? Let's go to amino acids and peptides. The genetic code specifies only 20 L alpha amino acids. Okay. Now again, I have to emphasize to you that whenever you say L or D, capital letter L or D, no, it does not mean levorotatory or dextrorotatory. Has nothing to do with that. This is only the placement of your amino groups, where it is found in the alpha carbon of the organic acid. Now, when you are talking about levorotatory or dextrorotatory, the sign there is for levorotatory is negative, and for your dextrorotatory is positive. Okay? All right, there are about 300 amino acids, but we have only 20 that are being used for making proteins. So that's why the genetic code only specifies for these 20 amino acids in human beings and most of mammals. But other species, alien species or whatever, they may have different genetic composition. So they might have different amino acids. No? But I think the amino acids, if you believe that we are being created by one creator, then the amino acids would be the same in all creatures, whether you are alien or not. But there are those that the bacteria, they might have some D amino acids. Ours are L. The configuration is L. Okay? And this is coded in the DNA, and the DNA, particular portion of the DNA or the gene is being translated or a transcript out of it, meaning it is being copied, and we have a messenger RNA. And the messenger RNA are now translated by your ribosome, 3 nucleotides sequence, no? In a sequence, constitute what we call a codon. That's why we call this triplet nucleotide, triplet or codons, or a 3-letter genetic code. And the genetic code, the letters there are corresponds to the first letter of your bases, the purine base and the pyrimidine base. Okay. All right, we will be doing a lot of this when we go into your DNA and RNA or nucleic acids. Okay. So for the moment, it says there are only 20 amino acids. And what are those 20 amino acids? We have it here. And they are categorized. No? Well, they are categorized. First category would be whether they are essential or non-essential. Now, when you say essential, meaning it means that your body
Need.
cannot synthesize them. So you must get it from the food that you are eating, or you get it from your diet. When you say non-essential, now when you say non-essential, it does not mean it is not needed. It means that your body can synthesize them. So there is no need to get it from our diet. Get that now. Essential and non-essential. There have been mnemonics that are being made for essential or non-essential. And the most common is private mathil, PVT-MATHILL. Private mathil, no? Or your essential. And if they are not found in the private mathil mnemonic, then they are non-essentials. Okay. All right. Another way is whether they are soluble in water or they are not soluble in water. So those that are soluble in water are called as hydrophilic, and those that are non-soluble in water are hydrophobic. Okay. Now, you should always remember that your amino acids, they all contain these two groups, carboxyl group and the amino group. Okay, attached to the alpha carbon. Now you should remember the alpha carbon is the first carbon after the carboxyl group. So that's the carboxyl group, that's the alpha carbon. Carbon after next this is beta and so on. Beta, gamma, delta, and so on. Like for example, this one. That's your carboxyl group. That's your alpha carbon. That's a beta carbon. Okay. Now this one. That's your carboxyl group. That's your alpha carbon. That's your beta carbon. No? So this is a branch chain. So this beta, two carbon groups are attached to your beta carbon. So you have two methyl groups attached to your beta carbon. You get it? Now, the carbons after the alpha carbon, this here, they are now into a group as R group, or sometimes called the side chain. The side chain. So your amino acid has this configuration. Alpha carbon, carboxyl group, amino group. So whatever is here, since this is not a carbon, this is not considered as a side chain. So this is an amino acid, it has no side chain or no R group. And it is the smallest if you compare it to others. Being the smallest have advantages. Because in the polypeptide chain, when the polypeptide chain is being bent, then do you find the amino acid glycine in that bent area? Because the space there in that bent area is very small, and this is the only amino acid that can fit in there. You get that? No? All right, so here, non-essential and essential. All right. And then the next classification is structural classification. So we classify them this way. We have the first group, aliphatic side chain. So it does not have a side chain here. What you have here is just only hydrogen. Now this one, you have a methyl group. Now this one, valine, has this. No? So this belongs to aliphatic side chain. Alanine, valine, leucine, leucine, and isoleucine. Aliphatic, all aliphatic. Now, the longer the chain, the more hydrophobic it is. Like that. This one. So it's hydrophobic. This one is hydrophobic. So you will find that the side chain in the polypeptide chain, once it folds, it is being folded to its natural state, you will find that all of the aliphatic long chain carbons will be found inside. And you will find this charge group outside or on the surface. Okay. Next group, with an OH. Okay. Now, the side chain of serine has an OH. So this makes it hydrophilic because of the OH. This one is partially hydrophilic because there's a carbon here without something that makes it soluble in water. No? And this one, tyrosine, we look at it with groups that are formed, no, with a phenyl group. So OH, with OH, serine, threonine, tyrosine. And then you have sulfur containing, there are two. You have cysteine, you have a thiol group, and then we have here methionine with a methyl thiol group. Now, because of this thiol group of cysteine, this is capable of forming a sulfur to sulfur bond with another cysteine. So that was what we call a disulfide bond, sulfur to sulfur. Then we have acidic amino acid with their amides. Okay, let's look at this. Aspartic acid, carboxyl group. It has two carboxyl groups. So that makes it acidic. That's positively charged, that's positive, or negatively charged, and this one is negatively charged. You will ask, why is this negatively charged? Oh, if you look at our other amino acids, carboxyl is negatively charged and your amino group positively charged. Because at 7.4, which is slightly alkaline already, the hydrogens here, or the protons, dissociate. And this amino group accepts a proton. And that's why it's become passively charged. So that's why we have a dipolar ion. Positive and negative poles. Okay, aspartic acid. So this becomes acidic because this charge and this charge here cancels each other. But you have one negative. Okay, so that's why this is acidic. However, this carboxyl group in your R or side chain reacts with an amino group. Reacts the amino group. And you form now an amide. And the amide of aspartic acid is asparagine. Glutamic acid, sama na may E. Lukso. Glutamic acid. So just like your aspartic acid, this carboxyl group in the side chain reacts with an amino group to form an amide. So the amide of glutamic acid is glutamine. Okay. Now, these are basic. Because you have here amino groups. No? Now this charge here and that charge cancels each other, but you have a positive charge here. Okay, that's arginine. So this is positively charged. Lysine as well, so you can see it here, positively charged. Histidine is also positively charged. It's positive here. Now, aromatic side chain, as you can see, this is histidine here, belongs to a basic group, but it has an aromatic side chain. This is aromatic. And we have here all aromatics. Phenylalanine, tyrosine, and your tryptophan. You have your, so these are all hydrophobic. Okay. So what do you think is the biggest amino acid? Huh? This one, TRP. Now, why do you think that the single letter abbreviation of tryptophan is W? This looks like a W, diba? Now, what about tyrosine? We cannot use letter T because we have already letter T, threonine. This goes for the Y here in tyrosine. Now this one, now this is copied from the book. That is TYR, ha? Dili na try. Unlike that one, that is TRP. That will be TYR. Now, why is this F? Because this is pronounced as phe, phenylalanine. Diba? Now, histidine goes with the first letter S. Now, why is this K? Lysine is K. We have already an L for leucine, di ba? That is K. Now, this one is R for arginine. Because we have already alanine, letter A, arginine. And then what do we have Q? Now in the alphabets you have K, L, M, N, O, P, Q. No? Your P is already proline. So you cannot use P for phenylalanine, so you use F. A, B, C, D, E, F. No? Okay. And then glutamic acid is E, asparagine is N, aspartic acid is D because there's already alanine for A. And then you have cysteine for C, M for methionine, and then your T is threonine, S is for serine, R is T, Y because this is already T, there's already another, there's already threonine, so R, Y, no? T, R, Y. Okay. Lysine G, alanine A, valine V, leucine L, and isoleucine I. No? Okay. So those are your amino acids. Proline, here, you have a pyrrolidine ring. So this is your alpha carbon, beta, gamma, delta. Okay. So you have 1, 2, 3, 4, 5 carbons. What amino acids have 5 carbons? Hmm? So let's start this one. 1, 2, 3, 4, 5. 5 carbons. Glutamic acid. Glutamine. 1, 2, 3, 4, 5. No? Histidine. 1, 2, 3, 4, 5. 6. No? This one. 1, 2, 3, 4, 5, 6. This one. 1, 2, 3, 4, 5, 6. Okay? Now, when we take up our metabolism, we have what we call amino acids with 3 carbons, amino acids with 4 carbons, amino acids with 5 carbons. And we call this a family. Family of 5 carbons, family of 3 carbons, family of 4 carbons, like that. Huh? So we'll go into that. Oh, here we are now, your hydrophilic and your hydrophobic. So these are all hydrophobic, not water soluble. There are group. Now, the group that gives characteristic to the amino acid, how many groups do you have in an amino acid? You have carboxyl group, amino group, and the R group, di ba? R group or side chain group. So which of the three gives the characteristic, chemical characteristic? Oh,
Group.
it's your R group. Because you have all of them have carboxyl and amino group. So they are the same. But they differ in their R group. So that's the one that defines the characteristic of the amino acid. Now here is one, selenocysteine. It's the 21st protein, amino acid protein. Now, although this selenocysteine is not coded in the DNA, it is, however, coded in the unusual tRNA, transfer RNA, called tRNA-seq, transfer RNA selenocysteine, and uses UGA as an anticodon, in which normally UGA is considered as a stop codon. When you say stop, that's the end of the translation, meaning it is a period. Okay, so they are debating on this. Because there are still researchers who says, no, we should not include that because it has no codon. Because all of the amino acids, the 20 amino acids have its own codon. But this one does not have. Its codon is a tRNA. It should be messenger RNA. Now this one is tRNA. Huh? Okay. Okay, this is ordinary cysteine. And this is selenocysteine with a selenium, a metal selenium. quite important. One function of your selenium is needed in the reduction of unoxidized glutathione. Now, what do you mean by post-translational modification? We mentioned this yesterday, di ba? On proline and lysine of your collagen. So post-translational meaning they're already, after translation, they're already now, the amino acids are already in linked together by peptide linkages before a modification is added. So that's why we call it translational modification. Now, yesterday we were talking about collagen. To become the proline that becomes hydroxyproline and the lysine becomes hydroxylysine. Okay. So they are, before it is released to, to become functional protein, there are modifications are added to it. So there are modifications like, for example, gamma carboxyglutamic acid. The carboxyl group is added to the gamma carbon. So that makes it now a carboxylated. So meaning to say that that glutamic acid, instead of having only 2 carboxyl groups, it becomes 3. The carboxyl group is being added. And the gamma carbon of your glutamic acid. Now here we are. Oh, addition of a hydroxyl group. That's your hydroxyl group. That's the hydroxyl group of lysine. This is proline. That's lysine. And this one here, down below, this is alpha carbon, beta, gamma. And this would have been epsilon carbon. Now there's an addition of a carboxyl group. So that your glutamic acid now has 3 carboxyl group. Okay, this is what I mentioned earlier, that a major containing amino acids, very similar to ours. Alanine, aspartic acid, glycine, isoleucine, leucine, phenylalanine, serine, threonine, tyrosine, and valine. And a non-protein amino acid, methylglycine, and beta-alanine. So these are all found in our body, all of this. So we don't know where that nature came from. Imagine that's 20,000 metric ton, which landed in Siberia. Okay, so we have more or less similar amino acids from outer space. We do not know where this came from, what particular planet which has this. So if we believe that presence of amino acids is in the proportion of formation of uh, living beings, whether they are bacteria or humans, then this gives us an idea already that more or less out there in space, if there is life, we have more or less similar amino acids. Now, these amino acids, the 20 amino acids, does not only mean that they are only made into proteins. They can be source of formation of very important compounds, like for tyrosine. They are precursor of thyroid hormones, tyrosine and phenylalanine for epinephrine and norepinephrine, and dopa. Glutamate is a precursor of GABA, gamma amino butyric acid. Ornithine and citrulline are found in this urea cycle for the formation of urea. And homocysteine and homoserine and glutamate gamma semialdehyde. And they are intermediates of metabolism of protein amino acids. Like for example, also like your arginine. Arginine is the source of nitric oxide, in which it is very important for vasodilatation or blood vessel dilatation. It is in fact our hemoglobin. Nitric oxide coming from arginine. Okay, so this also latherism, spastic paralysis of the legs brought about by seeds of 3 species of legume, lathyrus. So they can produce progressive irreversible spastic paralysis of the legs. Continuation of your laterosis. Okay. So homoarginine, it's being cleaved by an arginase, produce compounds that produce urolacterism. Beta ODAP is also a neurotoxin. So those are some amino acids that are non-protein. They They are not coming, they are not being used into synthesis of proteins, but they are found in nature. Also this one. So they are toxic materials found in plants. Now, we're talking about L amino acids. There are D amino acids found in some gram-positive bacteria. And amino acids and antibiotics produced by bacteria or fungi or reptiles and amphibians. Bacillus subtilis forms D-methionine, D-tyrosine, D-leucine, D-tryptophan. And Vibrio cholera incorporates D-leucine and D-methionine into peptide component of its peptidoglycan layer. As the bacterial envelope. Okay, amino acids may have positive or negative or zero net charge depending on the pH of the environment. Example, you have a protonic equilibrium of aspartic acid. So at different pHs, A, B, C, D, no? pH 1, pH 3, pH 6.8, 6 to 8, and pH 11. And you will have different species of your aspartic acid. Different species of your aspartic acid. Okay. So at pH 1, aspartic acid has a positive charge of 1. At pH 3, aspartic acid has a 0 charge. Okay. Negative and positive. That's cancel 0. Around 6.8, 6 to 8 pH, you have a negative charge. 1 negative charge. Negative charge here, only 1 positive charge. So that here you have 2 negative charges. 1, 2. Because your amino group loses its proton. Unlike this one, it is NH3, this one is NH2. So you have 2 negative charges. So different pH gives you different pH, different species of your amino acid. The pH in which you have a 0 charge, we call that the PI, isoionic pH, where the amino acid has a 0 net charge. The peak values express the strength of weak acids. Isoelectric pH or PI bears no net charges. The PKa values vary with the environment. The environment here is the pH, changes, no? pH of the environment. Solubility of amino acid reflects their ionic character. Okay. Oh, here you are. See here. It's the R group that determines the properties of amino acids. Okay. Amino acids that are already in a polypeptide chain is what we call the primary structure. The primary structure. Oh, here is our 3-letter abbreviation, single letter abbreviations. So this is read as glutamyl, alanine, lysyl, glycel, tyrosyl, alanine. All right, peptide structures, easy to draw. Some peptides contain unusual amino acids, yes. Like for example, glutathione. The glutamate in glutathione, because this is made up of 3 amino acids, your glutamate, cysteine, and glycine. The glutamate there is gamma carboxylated. So which means that that glutamate has 3 carboxyl group. And then glutathione has cysteine and glycine as the other 2. No? That's your tripeptide. So that is what is meant by unusual amino acids. No? So glutathione is an example. Oh, here you are. You have your glutamate. Now, this is your cysteine, it's your glycine. This is your glutamate. Now, when a peptide bond is formed, that's carbon to nitrogen, or what we call also as an amide linkage, form a double bond. Now, this forms like a double bond. No? It's only one bond, but it has a partial double bond character. Now, partial double bond character means that you cannot turn this around on its axis, this nitrogen or carbon, because it acts like this, 2 bonds. So you cannot turn it around. It is planar, so existing on one plane, but it has a double bond character. So that's your one amino acid linked to another amino acid. It is always a CN bond, that is your peptide linkage. This is a peptide linkage here, another peptide linkage, and another peptide linkage. Non-covalent forces, you have your hydrogen bonding, hydrophobic interactions, you have your salt bonds or ionic bonds, those are non-covalent. Saan niyo pagkuhan exam?
Mana ka?
Oh,
Next one.
sunod ang kaatin ako sunod-sunod.
Maputol siya. Kay, different din sila. Wait lang. Wait lang. Okay. Tuesday.
Okay.
Ano? Go.
Okay, so we go into proteins. Primary structure. Okay, importance. As you see it here, this is your ribosome. This is your messenger RNA. So your ribosome is translating the codons. Now these are already the amino acids that are being linked together by peptide linkages, valine, glutamine, phenylalanine, aspartic acid, methionine. Okay. And then once this amino acids has been synthesized, it is being folded. Okay. Then it is processed. Some amino acids are being, so processing, covalent modification involved, and then they are secreted, okay, translocated, then activated. Then if they are active proteins like enzymes, then they do catalysis, and the process of utilizing the same amino acid over and over again for catalysis, they become worn out, so aging, so deamination, so they are now targeted for destruction, no? So this, the whole protein now is called for destruction, and they are being tagged by a protein known as ubiquitin. So when ubiquitin attaches to your aging protein, they are targeted for degradation. In degradation, they are being degraded back into its component amino acids. And that amino acids that has been coming from the degradation of this protein, then these amino acids are again reutilized or recycled to form again another protein or the same protein. No? So it all depends on the demand of a particular protein. So what protein will be made? And because it is dictated by this messenger RNA here. So these are procedures used for peptide analysis. You know all of them already. You have this in your chemistries in your kindergarten. So let's go to higher orders. We have seen already the primary uh, order, which is just a sequence of amino acids joined together by peptide linkages and what we call a polypeptide or a polypeptide chain. Okay. So we have here configuration versus conformation and are not to be confused. When we say configuration, that refers to geometric relationship. Thus, we distinguish it whether it is L from D. While conformation refers to the spatial relationship of every atom in the molecule. So, when atom from okay. Proteins were initially classified by their gross characteristics. Before we call them fibrous protein if they look like fibers. Example are your collagen molecules because they are fibrillar. And then here is globular. Globular because they look like globules. Good example is your globin. That's the word there, globin, globular. Yeah. So gross characteristics, gross appearance. So we have four orders: primary, secondary, tertiary, and quaternary. Primary is the sequence of amino acids. Secondary is the folding of short, contiguous segments of polypeptide into geometrical order. And you can identify two structures there, alpha helix and a beta plated sheath. Alpha helix, that alpha and beta is just, the alpha helix comes first, always has been seen first, then the beta structure. So the alpha, that's the first structure that they have seen in the secondary. And you have now the next one, which is beta plated sheath. Tertiary is the assembly of secondary structural units into larger functional units. And you have different foldings, no? And component. And quaternary, when you have several subunits, two or more subunits. Like for example, your globin in hemoglobin is made up of four subunits, two alphas and two betas. Two alpha subunits, the same, and two beta subunits. And they interact with each other. If you remove one subunit, it is now non-functional. So it must be that there are four subunits. Okay? There are those proteins that have only two, no? Or three. So when there are two, you call it dimeric, and there are three trimeric, and there are four tetrameric. So tetramers, tetramers. secondary structure, so we mentioned that already. Okay, this is the alpha helix. So all those carbons and nitrogens are being shown. This is the axis, the central axis. You can have most, it is in a clockwise helix or a counterclockwise helix. But most common is the clockwise helix. Now this is the helix seen from the top. As you can see here, these are the R groups extended on the outside. So you can see that these perhaps are made up of amino acids that are hydrophilic. Because as usual, this area here, this area is aqueous solution. Aqueous solution. So if the R group is extended down there, in the central portion, that would mean that those amino acids are hydrophobic. So there you are. These are because as you see, it's a helix. It looks like a spring. So a spring can be extended or it can be compressed. Now to prevent that, hydrogen bonds are in place so that it cannot be extended nor can be compressed. Beta shape. Okay, so hydrogen bonds are being created in between polypeptide chain. Okay, so one polypeptide chain and another polypeptide chain and another polypeptide chain. So they are hydrogen bonded. Or let us say this looks like this is one polypeptide chain and going that way and then going this way. No? So one polypeptide chain. The direction is going this way, then it turns around and then turns around that way. Okay? This one here shows that there are three polypeptide chain and they are hydrogen bonded. Okay? So loops and beans are important here. What amino acids located at the bend or in the loop? They are usually small amino acid. And the smallest is of course your glycine. Well, you can also consider serine or alanine. So these are small. But the smallest is of course your uh, glycine. Tertiary and quaternary structure. So monomeric, only one polypeptide chain, dimeric. Now, when you say homodimers, it is made up of two polypeptide chain, but the same, meaning two copies of the same polypeptide chain. Just like when I said your globin in hemoglobin is made up of two alpha subunits. They are similar to each other. And beta subunits, two also beta subunits of the same kind. Okay? Now, if it's heterodimer, we can say that the globin is still a heterodimer because it's made up of two kinds, alpha and beta subunit. Huh? Okay? But the subunits, there are two that are the same, homodimers, and two the same beta subunits. Okay, now hetero meaning different subunits. Multiple factors stabilize tertiary. Of course, the non-covalent bonds come into play here. Okay, this is biophysical techniques to show. Okay. X-ray crystallography, nuclear magnetic resonance, spectroscopy, electron microscopy, cryo-electron microscopy, molecular modeling, and so on. Electron microscopy, I don't know whether UP has acquired a new one because what they have is not working. UP Diliman, but St. Luke's have two electron microscope. Protein folding. Important here is this, what are chaperones? Aside from proteins assisting in folding, chaperone proteins are the major assisting in the folding of the protein, chaperone proteins. Now, the folding of the protein is dependent also on the environment. If the environment is aqueous, then you have a different folding compared to if the environment is fatty or oily. Perturbations or disturbances of protein conformation may have pathological consequence like prion proteins, proteins that causes Alzheimer's disease and beta thalassemias. Beta thalassemias are those the beta subunit of your hemoglobin. The globin portion of your hemoglobin is defective. So they come up with what we call beta thalassemias disorders. Prion proteins, your mad cow disease. And you know this Alzheimer's disease. All right, collagen illustrates roles of translation processing. Okay, you have this. We have this yesterday. Your triple helix of collagen. All right, enzymes. What do we have in enzymes? Ano man eh? Oh, proteins. Let's look at myoglobin and hemoglobin first. Okay, this is your heme. This has your 4 pyrroles attached to iron. Iron has 4 ligands, meaning attachment, the 4 of which are attached to the 4 pyrrole rings. This one is attached to oxygen. Okay. So we have this is it. This is the heme cleavage of your myoglobin. The letters here are, of course, your helices. Alpha helix, beta helix, alpha, beta, helix A, helix B, helix C, helix D here, helix E, helix F, and this is helix G, and that's helix H. They're all continuous. Huh? Like for example, this F here, it goes this way. No, this stretch is not a helix. And then it turns into a helix, that's why it becomes G. And then that G goes up, which is not a helix, and then forms a helix again. And that becomes H. Okay. So that's just to identify the helices. F8 and E7 has a unique role in oxygen binding. This is very important. You have the proximal histidine, that's F8, and the distal histidine, E7. Okay. The iron moves towards the plane of the heme when oxygen is bound, and the movement is about 0.3 nanometers. So it is outside of the plane and it is moved by this movement, 0.3 nanometers or 0.3 angstrom. Okay, look at this. There is supposed to be, okay, this is carbon, this is CO2, no, this is oxygen and this is carbon monoxide. Now this is supposed to be, the iron is supposed to be outside. Huh? Yeah. Then once it is moved, when it is bound to oxygen. Now this two here is a comparison between oxygen and carbon monoxide. Now, this carbon monoxide binds much stronger to iron than carbon and than your oxygen. Okay. But when the carbon monoxide is bound this way, it is not straight like that. No, its ability to bind becomes lower than oxygen. That is the role of this histidine, to create something, no? So that this carbon monoxide cannot be in a straight position. Because if it is that is in a straight position like that, this is 77 histidine is not there, so it could be straight. And that ability to bind when it is straight is very, very strong. But once it is slanted this way, because of the space occupied by this histidine, its binding capability is much lower than oxygen. That is why, even though we are in a atmosphere where there's so much of carbon monoxide, just like in the street, because carbon monoxide is formed from the exhaust of those cars or jeepneys or trucks passing by. But we do not die of carbon monoxide poisoning because of the presence of this. There is carbon monoxide when you inhale, but it cannot bind because its ability to bind is much lower than the oxygen. Because this is a manner by which oxygen is very strong. But carbon monoxide should be carbon here and oxygen here. So it is straight. But because of the presence of this, there is no space for that. You get it? So you do not die just walking the street. But of course, if the amount of carbon monoxide is very, very high, then the possibility will it can bind. No? It can bind. Okay. This is the dissociation curve. Now you will notice that your hemoglobin binds oxygen in the sigmoidal curve. Because there are 4 heme that has to be oxygenated. While myoglobin, there is only 1 heme. Because myoglobin is only a singular subunit, no? It's only a singular unit, a beta subunit only. While your hemoglobin, the globin there, has 4 subunits, 2 alphas and 2 betas. And each one of them contains a heat in which it binds oxygen. And this one is only 1. So it is saturated right away, even at a very very small amount of oxygen. It becomes saturated right away. Becomes saturated. And for hemoglobin, it takes a while because there are 4 hemes that it has to saturate. Okay? Okay, hemoglobin is tetrameric. We know that already. This is hemoglobin. You have 4. This is 1 subunit. This is another subunit here. Another subunit. Another subunit. Different colors. But you have this heme here. And that is heme. That is heme here. And we have here 2,3-BPG or 2,3-biphosphoglyceric acid, which once it is bound to the globin, it stabilizes the whole structure, the presence of this 2,3-BPG. Now this is very, very interesting because it is only red blood cell that produces 2,3-BPG. You cannot find this in other tissues except in your RBC. myoglobin and the beta subunit of hemoglobin is almost identical. Almost, really the same, almost identical. Oxygenation of hemoglobin triggers conformational change. So, conformational. So, it is in space. And oxygenation of hemoglobin shows cooperative binding. Cooperative binding. Partial pressure, 50% partial pressure. Relative affinities of different hemoglobins for oxygen. You have fetal hemoglobin, you have hemoglobin A. Oh, here we are. You see this? Okay. The iron is attached to F helix F8. Now, once oxygen binds there, no, it pulls this iron or this heme to the plane of your pearl ring, porphyrin ring. Pulls it. So that's how it is. Oxygen here is attached. Okay, that is F8. The iron is attached to histidine. And the other one is oxygen. So how many ligands now has iron? There will be 6. 4 attached to the 4 nitrogens of your pearl ring or the porphyrin ring. 1 to the histidine F8 and the other is to oxygen. That makes it 6. Oh, this is what happens when an oxygen is bound to the iron. There is a movement. So this is alpha 1, alpha 2, beta 2, beta 1. So when oxygen binds to whichever, no, then there is a movement of 15 degrees. We call this the tight form, T form, where the 2,3-BPG is still inside. But when there is so much of already of oxygen, that 2,3-BPG is removed. And so this becomes now movable. And when the oxygen comes in, there is a movement of 50 degrees. And that movement breaks ionic bonds. These are the ionic bonds here. These red ones here, or salt bonds. Okay. Here is our deoxyhemoglobin. No oxygen yet. Now this is threatened. There is oxygen already. So look at this. This becomes wavy. This is the hydrogen or the ionic bonds or salt bonds are already threatened. More oxygen. All right. On the other subunit, and this is broken. Then another oxygen comes in. These are broken. It's only being held here. No? And then when there is another oxygen, then all of this, or Or either from here it could jump into here, or this one could jump into here until you have all the hymns being oxygenated. And you will notice that there is already no more what you call ionic bonds. No more ionic bonds. No more ionic bonds. However, when this is released to the tissues, the oxygen, then ionic bonds are restored like this. Comes like this again. So when this goes to the lungs, where oxygen concentration is very high, then this is what's going to happen. It's going to break all of those hydrogen bonds to make it easier for oxygen, you know, to fill up all the heme molecules. So your what you call your 2,3-BPG is removed as long as there is a high oxygen tension, and that only happens when it is in the lungs. But when it reaches an area where oxygen is low, this oxygen now in your heme will go to the tissue where it is deprived of oxygen. And 2,3-BPG are reinstituted as well as your salt bonds here. Okay? Hemoglobin also assists in the transport of carbon dioxide from the tissues through your enzyme carbonic anhydrase. Carbon dioxide plus water becomes carbonic acid, and then spontaneously bicarbonates because of the pH around, and this is the one that is being carried as a bicarbonate towards the lungs. So this is in the tissue. Oh, this is where it is now. All right, from the tissue, you have carbon dioxide and water, then you have carbonic acid, then it is carried by, all right, and the hydrogen is also carried, that's the protons, and then interacts with oxygen in the lungs, then there you are. The hydrogens are released together with the bicarbonates, that becomes carbonic acid. The carbonic anhydrase in the lungs breaks it into carbon dioxide and water. And this is exhaled as carbon dioxide and together with the moisture, water, every time you exhale. Okay? And that is what we call the Bohr effect. Carbon dioxide generated in the peripheral tissues, and it is exhaled through the lungs. So protons arise from rupture of salt bridges when oxygen binds. So protons are released. 2,3-BPG, internet connection is unstable. This is your 2,3-BPG, which stabilizes. Now this is contribution from one subunit, another subunit, another subunit, another subunit. Okay, so this is now stabilizing your globin molecule. adaptation to high altitudes. In high altitudes, there is less oxygen, of course. No? So the body compensates by increasing the number of red blood cells. So there is an increase of erythrocyte when you are living in high altitudes. And when you come down into the lowlands, then it shows, if you are a fair-skinned individual, it shows that you are flushing in your face because of high erythrocyte content of oxygen. There's an increased number of erythrocytes, and there's so much oxygen in the lowland compared to the highlands. Numerous mutations affect your hemoglobins, have been identified. You have your methemoglobin, hemoglobin M, and hemoglobin S. Together they form hemoglobinopathy. Hemoglobin S is your sickle cell anemia. This is brought about by a change of one amino acid in the beta subunit. That's supposed to be glutamic acid. Number 6 amino acid on beta subunit is being replaced by valine. And there's a big difference between these two. Glutamic acid is polar. Valine is non-polar. So it changes the surface of your hemoglobin, of your globin portion of your hemoglobin. Okay, this is sickle cell anemia, hemoglobin S. As you can see here, there's a complement. No? This is the complement. So when you stack this together like that, no, then all hemoglobin are stuck to each other. And this occurs during the unloading of oxygen. You have your deoxyhemoglobin. Okay. And since this is a hard particle, they usually occupy a space along the inner surface of the membrane of your RBC and forming like a half moon, a crescent moon. And it is hard. So when this erythrocyte passes through very, very small apertures or holes, they squeeze itself so that they can pass through. But that hard particle, this one, will know, be responsible for tearing the cellular membrane of the RBC, and the RBC ruptures, and that causes the anemia. This occurs in the spleen, because the spleen is, of course, look as the structure there is like a filter, very, very small holes. And your hemoglobin has to pass through there. I mean, your RBC has to pass through there. But the hemoglobin has already hardened on one side. And that would, of course, rupture the RBC. So, medical increase, myoglobinuria, anemias, and thalassemias. Thalassemias, as we said here, beta subunit, no? And this one is when you have too much sugar, your hemoglobin will be decorated with sugar. In this case, it's